This. Hmm. All right. Okay, I'll continue what we were studying last time. It's kind of important, and the mathematics is not hard, but it's just a little bit confusing. All right, so we'll learn a unitary matrix today. So what I showed you is when you like make this kind of rotation for geometrical vectors, there are two ways of seeing it, right? You already have experience in high school. One is like you're using a new axis so that the same spot, okay, the same spot actually doesn't change. The point itself doesn't change, or you can equivalently say it as a vector. It doesn't change, but your coordinate looks different. But actually your dot is staying the same. That's the first concept. Second concept is that you are actually rotating your vector, okay? You're moving your point from here to there. There are two concepts, and then what is that? You use unitary matrix to describe both, okay? But their meaning is different. Let me write it. So it's basically analysis from different viewpoint, okay? You just change your axis, okay? You look at like this way and that way, but the thing is the same. That's one. And let me give an example. So in particle in a box, we actually worked with the Hamiltonian eigenbasis, right? So each state we calculated, right, the sine kx over L, that was that was energy eigenstate, right? It has a specific number for energy. But actually, the same thing can be seen from X eigenbasis, right? X eigenbasis, the same particle in the box, for example. So H eigenbasis, we used to do something like this, right? So this psi I is a energy eigenstate. It has a specific energy, and you have a like linear combination of energy eigenstate, but at the same time, it is some kind of function like this, right? Psi x. Psi x, we were using this psi x, right, as a function. And then this is in fact an expression of linear superposition of x eigenstate. So let me write down the equation here. So what is the x eigenstate? Delta function, okay, in x. Delta function in x is eigenfunction, is what is that? It's an x eigenstate, but we have to stick with the delta function because x is a continuous variable, right? So x eigenstate is something like this. And then its coefficient is a psi x prime, all right? And then this is what? This is a linear combination of delta function with its own coefficient, right? So it's a linear combination of x eigenstates. And then this equation is showing that how you describe it as a linear combination of energy eigenstate. At the same time, that is the same as linear combination of x eigenstates. Okay, so it's a bit confusing because I'm using continuous variable x, but actually they kind of mean the same thing, right? Integral is the summation. So another number two, rotational vectors. So when you usually say unitary transformation in quantum mechanics, usually it is used in this context. Unitary transformation is basically representing the quantum state change or evolution, which we have learned. Quantum state evolution, which is like meaning the changing over time, evolution. So let's look into details of what we were discussing. Change of basis first. Represented by unitary operator. All right, so let's say the same quantum state I was describing with the basis of psi, okay, psi and basis. And then let's say there are different complete sets, which is phi. I want to describe in phi basis. And then how do you find out it's a matrix representation? So that's the question. So let's say there is this quantum state. And then let's this one, 1 second. C J psi J, okay, J. But at the same time, with a different basis, you may want to write it in terms of DI phi I, right? The same quantum state you can express in both, like both bases, okay? So it's the same, it's kind of the same thing as what you just saw here, this one, right? The same spot, 1 sec. The same spot X, right? It can be expressed in terms of a V1, V2 axis or U1, U2 axis, okay? It will give you different coordinates. You will have a different CI and CJ and DI, but but they actually mean the same quantum state. And the question is, let's say, okay, so I have, so let me put alt here to make sure what we're discussing. So let's say this is something like C2, the column vector, right? Something like this. And then now I want to use a representation made with the new basis, okay? New basis, how do I do? Let's say I want to write it as this is new, and then this is written in terms of a phi basis, and then it's going to be D1, D2, right? D1, D2, so on. And then the question is, okay, how are you going to relate CIs and DIs? Okay, they're not like random. They are related by some relationship. How do I find it? So that's the question. So to do that, let's do like we're going to use what we already know well. Okay, let's start with something very simple. So instead of like dealing with the general stuff, let's start with something looks very simple. One of the basis function, okay, the first basis function in psi. And then you can imagine it's possible to expand this in terms of phi, right? Okay, right? So I've said phi is a complete basis. So any quantum state you can expand in phi basis. Okay, so that's what I did. I introduced a new coefficient alpha. And then we actually learned already how to extract the coefficient from that kind of expression by doing what? By using orthogonality, right? You apply a bra of phi j, 1 second, phi, you apply phi I to the left-hand side, you can extract, right? You can extract alpha I, right? So I'm assuming it's all normalized, so you know how to calculate this. Okay, so using this fact, right? Using this fact, what I'm going to do is, so let me do it one by one. Alpha j phi j j, right? to do this, to I'm applying phi I to this entire thing, right? I'm applying bra, and it's going to extract only the coefficient you want, right? Alpha I. You extract alpha I. Okay, so we actually know this one is change at least, right? This column matrix 1, 0, 0, so on. This column matrix, right? We know this is changing to what? We know this one is switching to with the new base, it's going to be alpha 1, 2, 3, and so on, right? It will be this one. This is with the psi n basis. The underlying basis you're assuming is different, right? They're two different things. And then phi, this one, alpha, we already calculated. Phi 1, psi 1, phi 2, psi 2, right? Phi 3, psi 3. Right. I'm just doing the simplest example of psi 1. I want to write down psi 1 in phi basis. That's how you calculate. Okay, so next one, let's it's a kind of a stupid repetition, but let's do it again just to make sure we know what we're doing. Psi 2 is going to be, I can say it's a beta j phi j, right? It's another coefficient. And then likewise, you can just do this, right? To calculate beta, you can just do this, right? So it's all repetition of the same thing. Psi 2 used to be, here is what, 0, 1, 0, so on, right? Second is non-zero. It's just 1, right? Second coefficient is 1. This is in psi n basis. And then it's going to change to beta 1, 2, 3, 4, 5, right? Beta 1, beta 2, beta 3, so on. Which is what? Phi 1, psi 2, phi 2, psi 2, psi 2. Okay. Pay attention to indices I'm using. All right, don't get confused. So this is written in terms of what is that? Phi n basis. Okay. Right. So now you can see easily this can be extended to any psi basis, right? Okay, so let me write that what we did in terms of in terms of the linear algebra expression. So let's say I am given this quantum state. To make the notation simple, basically I'm just removing the sigma sign to make things simple. So this one, right? You can write it as this. And then this will change to what in phi basis representation? As you know, right, this one is in psi n representation. And then we just saw each of these are changing to what, right? We just saw how we did. So this one will become C1, phi 1, psi 1, phi 2, psi 1, okay? These indices can be confusing, but if you follow one by one, it's okay. Phi 1, psi 2, phi 2, psi 2, right? In new representation of phi n, 1 second, let me use the color code. Phi n basis, it changes to that expression, right? Okay, so to wrap up, di is value of ith row, okay? Di is the value of ith row in a new basis phi. Okay, that is going to be, so you can, for example, take a look at this, okay? Di, in this case, it's basically you are adding this and that, right? Then you get D2, right? Let me write it down. JCJ phi I psi J. One second. Little CJ. CJ. Okay. Phi I psi J. Okay, it is correct. It is correct. Okay. So what I wrote that is like basically this expression. Okay, I'm adding these two terms. Okay. So I'm using sigma sign. And then let me mark this number. Okay, it has two indices, I and J, and it's a complex number. I say it's inner product result. So let me call it Uij. So it's going to be J Uij C J. Okay, and then once you see this expression, right, it's something you already have learned. It's a matrix. It's linear algebra. It's a definition of a matrix definition. Right, the way you calculate the matrix is exactly that, right? So that U, right? That U, if I make the matrix collection of that Uij, let me call that U matrix or operator like this. Or what I'm saying is something like this. U1 is the usual notation. U12, U21, U31, U22, and so on, so on, so on. Okay. So that's U, right? Uij is defined as phi I psi j. Okay. So you can calculate Uij. Okay, and then let's define that U matrix like that. Right, then we're done. Then you can just use that U to convert from C to D. So basically, you just need to multiply U to the old representation. So to make things simple, let me stick with a 2 by 2 example. U21, U22, C1, C2, U11, C1, U12, C2, right? U21, C1 plus U22, C2. Okay. So that's how you usually do your matrix multiplication. And then this one, U11 is what, according to our definition, is this one. This one is phi 2, right? Phi 1 psi 2. Okay, phi 1 psi 2. C1 phi 2 psi 1 plus C2 phi 2 psi 2. That's calculation we're doing. That's going to be D1, D2. It's a new matrix we were looking for. All right. So let me wrap up. The exact same quantum state. There is one way of writing it in matrix form using this basis, psi. And you can also use another basis, right? Another basis, phi. And then they will have a different coefficients, right? C and D. And then among them, right, there is a conversion matrix. The conversion matrix is having this form. This form. Okay, that's how you convert from this basis to that basis. So once you know the basis, right? Know two bases, you know you can extract U, and then you can convert any quantum state in a new coordinate system. Okay. So this is how you get the coordinates of a given quantum state. And then let me move on to another interesting subject. So the title is linear transformation. So basically an operator. The linear transformation in matrix is a square matrix, right? So this matrix. So you convert it's like this is a fed matrix, it's rectangular, and then in a new basis. Let's say I have this matrix, and then any matrix, right, in quantum mechanics, you are assuming some sort of basis. And this matrix, right, if I use another basis, it may look different, right? Okay, so is there going to be another new matrix? It means the same operator, but its numbers in its row, its elements, right? They're different, but they are related, okay? How? That's what we're going to see. All right. So according to what we just have seen, right? Okay, if you apply this U matrix to your old representation of matrix, you're gonna get new representation. And then let me write. So there is an operator Q, right? Operator Q, let's say. This operator I apply to this one. It's going to be that one, okay? The psi becomes phi. But pay attention to this labels, all right? This really means that you are changing from quantum state from here to here, okay? This one is what we just saw. This matrix basically the same quantum state you're representing in a new basis, and then that U, right? Okay. It's a new basis. To convert the coordinates, what do you do? That's U. This Q is something like real action, whatever operator, okay? Differentiation or whatever, okay? Multiplication, it's an operator action. So that's what Q represents. And then let's say this phi old is still old representation, right? It's basically the matrix you should interpret it as okay, this is written in basis of the old basis. So you can also convert that into a new basis. This time, quantum state is not changing, okay? Quantum state is not changing, you're just changing the numbers in your matrix. So that's this. And then, okay, but what I'm saying is in the end, right? This old and new just means that the same thing with a different representation, okay, different basis. But psi and phi are different quantum state, okay, they're two different things. Okay, now the question is, all right, let's say this Q operation is getting done within old representation system, right, old basis, and then the same operator, okay, same operator, the same Q, it's not different, okay? It's the same Q, but what if I write this in a new coordinate system, okay? That I'll call new, and then that's going to convert psi new to phi new. Okay, first of all, you need to understand what these four mean. Second, what I'm going to do is that now we want to figure out Q old is changed to Q new. In what way? Okay. Q old, Q new, what way? They are related, right? They're the same thing, but with a different basis. How can you find, right? So previously we just found out how to do it for a given quantum state. Okay, we found the conversion formula for an operator this time. Okay, how do you convert? It's this new question. Okay, so let's do one by one. It's very confusing. So we will evaluate this expression. Okay, sandwiching the operator between this. Okay, so this one, let's go one by one. First, what I'm going to do is I'm going to convert. Okay, phi nu. Yeah.
I think there's a typo over here, or 5 ohm to 5 ohm.
Oh, right. Thank you. Typo. Let me fix. Phi new. It needs to be new. Right. New. Okay. So using those four equations, right? What I'm going to do is first I'm going to replace phi new with the bra and cat side, left and right hand side to an old representation. Okay. U old. And then I didn't touch this operator here. And then this one is U psi old. Okay. That's the first step I've done. Next step, what I'm going to do is I'm going to move this U, right? U into middle, right? We have learned the rule how to do it, right? So if I do so phi old, U goes there when you take the complex conjugate, right? So U dagger and then Q nu, it comes before Q nu, and then U just comes, right? The right hand side that just comes in the same shape, and then it comes like this. And then the last one, right? So I'm keep telling you this new and old, they just mean the different representation, okay? Different representation, but they actually they are the same thing. The thing is the same. You just read it from the different coordinate system. The thing is the same. So if I do this, let me write this down. Phi old, Q old, psi old. I can do it because this one and this one, they're supposed to be the same. Okay, whatever has a new label, old label, they are the same thing. So they are the same thing. Their inner product needs to be the same. Okay, let me give you a quick example. You don't need to just don't need to write maybe. Let's say I have a vector, these two vectors. Okay, so you guys know how to calculate the inner product of these two like blue vectors, right? You did multiply its length and then the cosine theta, the angle, and then that number, whatever inner product you calculate, right? It's not going to change if I use this read their numbers with this new coordinate system, right? The inner product doesn't change. Inner product is inner product, right? So, but when you actually calculate, the procedure will give you basically like new coordinate system, right? This dot is, and this dot is like this number and that number, but all the basis is like this number and this number, right? The procedure may be different and you can follow the inner product rules, but in the end, you are supposed to get the same result. Why? It's just the inner product between these two vectors, okay? It shouldn't change when you change your basis, right? It's the same thing. So this operation, right? This is basically your quantum state, the same quantum state, same operator. They are supposed to be the same when you do this calculation. So now we're done because you just compare these two relationships, these two, right? Same, and then this one is this. Okay, we found the Q new and Q old relationship. So Q old is U. Okay, that's how you get a new representation for an operator. And then you can do this simple calculation to get the reverse relationship. Okay, so let me do it here. you just do this, okay? Right? You apply this, and then you can do the calculation with this order. And then this was U dagger is what it's an identity matrix. It's unitary transformation, right? U was unitary. So they are identity matrix. They're both identity matrix. So you get Q new. Okay. So Q new, you can write it as U, Q old, U dagger. All right. So we have shown how to convert the numbers of the matrix from this basis to another basis. So that was an abstract way of writing it. So let me give an example of a real linear transformation and linear unitary transformation and the basis rotation. Okay, so this one. The angle is a little bit. Okay, so I am using two bases, okay? So black and blue one. Black, I'll call it U1 axis and U2 axis. And then the blue one, I'll call it V1 axis and V2 axis, okay? And then to make this example, I'm using 45 degrees to make things simple, all right? So there are two bases. Bases are given, and then unitary transformation I want to discuss here is, let's say, I want to do this. I want to discuss this transformation. Let me say my input is this dot, which is x comma y. And the unitary transformation is what it's really changing the quantum state, okay? Really changing your vector to something else. What I'm doing is that this mirror operation, okay, with the V1 axis. All right, and then this x comma y is read from U1, U2 coordinate system, all right? U1, U2 coordinate system. So, and then that's a V1, V2 is a 45 degrees. So you actually have learned, right? This mirror operation is doing what? It's a swapping y and x, right? You're very familiar with it. So let me write this down, y comma x, okay? Y comma x. So let me write this down. My unitary transformation, one second, u is okay, one second. Let me first, and then you can imagine, right? You can imagine this one will be read by x prime comma y prime, okay? When you use blue axis, right? The numbers can be different, but it means the same dot. And then this one is going to be read as, what's going to happen is that, okay, this one, right? And then you're using this axis to make a mirror. So actually from this axis viewpoint is that you don't change your x coordinate, you like flip your y coordinate into a different sign, right? So this one will become minus y prime, one sec. Okay. So that's, you kind of know, without calculation, you kind of know already because it's a very simple example. So we will see if this transform is a basis rotation and unitary transformation is really working with our formula. Okay. So let's do one by one. So U, right? I have been using U as a coordinate transformation and Q as an operation. Okay. So U as a unitary transformation. And then, so my input is 1, 0, basically some point here, right? And then this one, basically this is a C1, C2 I'm talking about in this scenario, okay? C1, C2, and I wanted to find D1, D2 is appearing as a what number, right? In a new coordinate system. So we kind of know the answer already. It's going to be 1 over square root 2 minus 1 over square root 2, right? Think about this dot, right? One sec. This one is not this one. Right? Some dot here. Try to read with the blue axis, right? It's going to give you that. So, and the next basis of U1, U2 axis is a 0, 1, okay? And then this is what? This is 1 over square root 2, 1 over square root 2, right? This both positive signs. And then we define Uij as this, right? Phi I psi j in our formalism. Right? So let's see if this really works. U is going to be, one second, this one is coming here, this one is coming here, right? For U. So 1 over square root 2 minus 1 over square root 2, 1 over square root 2, 1 over square root 2. This is U, okay? That actually should match the formula you have learned from high school, the rotation basis was the axis rotation, cosine and sine expression is the same. And then this I is a row index, J is a column index, okay, as usual. All right, that's U. And you can check if these numbers are making sense, all right? You can take the inner product of these two, okay? Psi 1, phi 1, psi 1, psi 1, phi 2, phi, was it? It's so confusing. Anyway, you just like swap indices 1 and 2, right? There are 4 combinations. And then you actually can carry out geometrical, what is it? Geometrical inner product, and then you'll get that result, all right? And then let's look at the operator. Q old is you have a 1, 0. What you're going to do is a 1, 0, right? You're swapping x and y because you're doing reflection with the 45 angle line. So if you do this and then Q old, in old axis you have you're given 0, 1, right? And then you'll get 1, 0, right? You can see that, right? The dot here comes here, right? This equation is the dot here goes there, right? For that reflection. So Q old itself is this matrix, right? In the old representation, old axis, U1, U2 axis representation. So to generalize, Q old, when you apply to XY, it's a reflection against the 45 angle, right? The line. So it's going to be give you YX. Okay. So let's see Q new. According to what we have learned, it's supposed to be this equation, right? Sandwich between U and U dagger. and then see if it really works, because we already know U, Q old U already, right? U is what? 1 minus 1, 1, 1. I took out the 1 over square root 2, and then 0, 1, 1, 0. And then if you take the complex conjugate of that U matrix, you get this one, right? You transpose, so minus 1 and 1, swap the location, and then you carry out this calculation. Square root 2, both of it, I take it out as a half. And then let me see, let me first calculate first two matrix. 1, 1, 1 minus 1, right? I calculate the first two terms here, and then I get the leftover is this one. Then what do I get? I have a half, 2, 0, 0, right? And then minus 2, 1, 0, 0, minus 1. All right. So Q new, if I apply to some coordinate, I think to make things clear, I'll do some color coding here. Okay, so I'll use this blue one. I apply Q here. 1, 0, 0, minus 1 apply to x prime, y prime. X prime, y prime is read from V1, V2 axis, okay? The numbers are coming from that blue thing. And then what do you get? It's going to be x prime minus y prime. Okay, that's what we would expect from geometrically, okay? So this example has everything we just learned today. How you think the concept, all right? If there's a rotational basis, there is this given operation that is reflecting over this line. And then that reflection is the thing, right? That itself is just the reflection over that line. But in the black axis, if you use the black axis as a basis, you have this sort of a representation. But if you use the blue axis, you are expressing this way. They look like completely different matrices, but they actually mean the same thing. But they are built upon different bases. Okay, so next one. Okay, it's very confusing, but I think whenever you get confused, just go to that slide, okay? That has everything as a tangible example. So let's keep continue when we actually do a transformation of a quantum state. Transformation of quantum state. So quantum state is vectors, right? So we will see how we handle. Okay, so let me bring up the picture notation. Okay, so far we have been discussing both concepts. You are changing, okay, U1, U2 to V1, V2 axis, right? Even the same vector reads with the different numbers. And also there is another concept of you're actually changing X to Y. Okay. You are changing that red thing to blue thing, okay? You're actually changing quantum state. There are two different quantum states. So when all these things are mixed and combined, how to handle, it's here, psi nu, right? Psi old. U is the one allows you to change its coordinate system, but the same thing. Phi new, U, phi old. Okay, you just change numbers. Okay, so then using these setup, right? I'm going to show you the property of this transformation matrix, and I'm going to prove that it's a unitary. So what I'm going to use is, if you have two operators and then take the complex conjugate, right? It's a matrices, so you swap its orders and then apply, right? Apply in a reverse order, but each of them have a complex conjugate. So given that, right, you also can calculate something like this. So matrix is applied to a column vector, okay? So still it's a matrix. Then you take the complex conjugate of the whole thing, and then this was a cat becomes bra, and then A will have that, right? Okay, so in matrix, we already have seen this quite a bit, right? A, B, when you have a transpose, you do B, A transpose like this, right? So you guys know what it is. And then there is another thing, we already have learned this, but let me just write it again. Phi nu bra is what? Phi nu cat's complex conjugate, right? And then phi nu was U phi old, right? And then the complex conjugate. And then you also can write it as phi old as a bra and U operator dagger. All right, it's all about matrix manipulation. So given these, right, given these, what I'm going to do is I'm going to calculate the inner product between phi nu and psi nu inner product, okay? It's similar to what we have done in the two slides before this. So phi nu here, you can write it phi old U dagger, right? Okay, and then psi nu, I wrote above there, it's a U psi old, right? Okay, and then, so if U is a unitary matrix, right? Unitary matrix, then phi old, if U is a unitary matrix, then it means that by definition, it's an inverse matrix, right? And then inverse and U, so it's an identity matrix. You are proving that, okay. So let me wrap up, right? If you have this relationship, right? And then if you assume, okay, if you assume U is a unitary, then actually your inner product doesn't change. This is no change of inner product is quite important because we will learn it very soon because the inner product actually in quantum mechanics is interpreted as some sort of like probability sometimes, okay? Probability amplitude. So these numbers shouldn't change and you change basis, okay? So, and then if you extend it to phi nu is actually the same thing as a psi nu, you can calculate. Doesn't matter new basis or old basis, right? As long as your basis rotation is unitary. And then the inner product doesn't change. And then this self inner product is length squared, right? It's this concept is the same as a geometrical vector, but it can be extended to a general concept. of a linear algebra vector, quantum mechanics vector. So this is no change of vector length. No change of vector length. So unitary transformation, the change basis, right, doesn't change the length of the vector. Okay. And then that's quite important because Born rule. One second. Sorry, actually, when I explained these things, I actually made a little bit of an error. So what I meant here is that this U matrix, right? I meant actually in my note, I meant as a actual transformation, not this one, basically. Okay, sorry. Sorry for confusion. I actually meant this one. Okay, not this one. But I explained it as a left one, but I meant this one on the right-hand side. So this whole note is written for this right-hand side U. Okay, so notation can be a bit confusing, but what I meant is that I wrote this note a long time ago, so I forgot. But then it is U is basically you're really changing the old vector to a new one. And then in this case, if it's unitary, it doesn't change the length, okay? Unitary transformation doesn't change the vector's length, even if you change the quantum state to another, right? This is not the basis of, okay, let me be clear. I meant this on the right-hand side. So in that case, right, Born rule, if you remember, Born rule is dictates normalization condition, right? The way we interpret quantum mechanics is that absolute square, right, is like the probability density. So we have learned this, right? And then this one, the length square, right, is supposed to be this expression. Also in bracket notation, you can write it as this. And also in energy eigenstate notation, we already have learned this, and then this is supposed to be 1. Okay. And then that doesn't actually can be any complete set. So expanded in a complete set. All right, so then what I'm going to do is I want to say that if I change quantum state, okay, let's say let's be more specific, it's an electron. Let's say it's an electron, and then I want to change this electron's quantum state into something else, okay? It can be anything, but electron is there. Then whatever new quantum state, right? It still needs to satisfy Born rule and needs to be normalized, right? Because electron is there. So if you add up all the possibilities, it needs to be added up to 1, right? So in that sense, your transformation from this quantum state to another quantum state, it needs to keep its length. Okay, you cannot like randomly change its length because then you start breaking the Born rule interpretation, probability interpretation. You cannot really, change it. Okay, electron is still there, so your probability has to add up to 1. All right, so the phi quantum state you apply to this one, and then you get new quantum state, and then you can expand it in psi basis, okay? So then this one, inner product of this new quantum state is going to be something like this, right? In a complete set. And then that's new quantum state, okay? Electron has changed it to no quantum state, but it's an inner product, okay? Self inner product is always has to be one before and after changing. Okay. So, okay, starting from a proper quantum state, right, whose length is one. If you have this quantum state, that is a physical one, okay? Electron that makes sense. You can use the apply Born rule to this quantum state. And then to this one, if you apply some unitary operation, what is that operator, you apply to it and get new quantum state phi like this, then your conclusion is that so new quantum state also has length of one, right? If you have a unitary operator, then if you apply unitary operator to a proper quantum state, and then the output is also a proper quantum state, you can apply Born rule for interpretation because it doesn't change its length, okay? So geometrical example, for example, if I have this quantum state, right? And then if you change something like this, it's not unitary transformation because the length is like 3 times longer now, right? It doesn't fit the quantum mechanics formalism. Quantum mechanics formalism has to work with the Born rule. You have to apply this probability interpretation. Then you cannot, your quantum state, the proper one here, cannot change to something like that. Okay, it has to keep its length. And then, so I will use another logic. Let's say quantum state phi is a result of a transformation U, okay? And then their length is both one. I'm doing the logic, following the logic in a reverse way, okay? So the arrow direction is the reverse what I'm doing, okay? I'm not talking about U is something. I'm not assuming U is what. But there is this transformation. There are two quantum states. They're both length is one. And then the transformation U is there. Then actually you can prove that U has to be unitary. So it's if and only if relationship. Okay. So, but then if the bottom line is you just remember quantum state change to one to the other, you always work with the unitary transformation. There's no exception, all unitary transformation. Otherwise, you're going to break the rule of the Born rule. Okay, so let me give an example of, it's a kind of highlight of the unitary transformation because, okay, what is the good example of unitary transformation? You have some quantum state and then you don't do anything, let it go, right? Let it go. It's a time evolution. The time will just flow, right? And the quantum state will change into something else. That's unitary transformation. So the example I'm using is a time evolution as a unitary operator or transformation. Okay, so we already have learned in the beginning of our class, right? We have a time-dependent quantum state, and then something like particle in a box, you have a complete set, you do expansion, right? As an energy eigenstate, and then you have this spatial function and the time domain function, right? And then the phase evolution is expressed as that, right? We have learned that equation, okay? Each energy eigenstate is evolving the phase, what is that? The frequency is different, right? It's proportional to energy. That's what we have learned. And then, right, so once you figure out at some moment at time 0, you know what it is, right? You know all the coefficients like this. And then you know it's an evolution over time completely. Okay, that's what we have learned. We just reviewed the equation. Okay, so but also you can interpret this as this was a quantum state at this moment t0, and then after some time it was linearly transformed to psi t after time t. Okay, by after some time it evolved into some new quantum state, right? It looks different, right? You have this time dependence. So it evolved to something else. Let's see it's a unitary transformation. So I'm going to write after some time t, it evolved into a new quantum state starting from this input, okay? And then the transformation I'm writing as u, but I put little t there because it depends on time. So then in this case, ut is what? Okay, is it really unitary transformation? So we will see, all right, if it works. So let's go back to our original time-dependent Schrodinger equation, okay? So this was our starting point. And then that operator is a Hamiltonian, right? Hamiltonian, they're representing energy. And then what I'm going to do is I'm going to apply that to like Schrodinger equation, all right? I'm applying that to that equation. So if I do some substitution, let me write down I h bar u t quantum state at time t equals 0, and h is here, and the u t quantum state, okay? Okay, so then, right, it's kind of this equation quite general, right? Quite general equation. So this one is some can be some quantum state, right? And then you are applying this operator to that and this operator to that, right? And then they are always the same. So, and then as a conclusion, what can you say? You are saying that these operators are actually equivalent, okay? This is an operator, okay? It's not a function, it's an operator. This operator is same with this operator. All right. And then, right, 1 second. Let me update this. So to clean up left-hand side, I'm only leaving the differentiation as a function of time. And then the IH bar, I'll send it to the right-hand side. So minus IH bar H operator U T, okay. And then this equation, if you look at it, right? Oh, it looks very familiar, right? It looks very familiar because you take the differentiation as a function of time and you get yourself with some constant multiplied, right? The only caveat is, well, the ut is not a usual function you are using, right? And then the h is not a usual number you were using. Okay, they're all operators. How can you solve this problem? So there is a way to solve this problem. In fact, right, the shape of the form, 1 second, the answer to that, right, is that, well, you just do the same thing. Okay, that's an answer. It's the same as you usually do. But remember here, right, you actually define, okay? Okay, what do you mean by putting operator on top of the exponent, right? There, right? How can you usually you put number, right? Exponential number. And you guys know how to do with the real and imaginary numbers if an exponent has a number, right? Complex number. But probably first time you're seeing that operator is there. How do you do? Well, there is a definition, okay? Definition of how you calculate this. All right. So let me show you a definition. And then the definition is very much inspired by the exponential function, okay? So in the Taylor expansion, so if you remember, I theta, if you do expansion, right? Taylor expansion is giving you this, right? 1 second. Minus I, minus I. And then this one, also you can write it as cosine the Euler formula, right? I sine theta, and then sine theta, cosine theta, Taylor expansion, and do the same thing. You just recover that exponential, right? So this is what we are familiar with. And then we will apply this here. Okay, exactly the same, except that in the place of a theta, I'm going to put H operator over H bar T. Okay. Oh, okay, and also minus sign. So if you do it, 1 second. I can write 1 in the place of 1, but actually left-hand side is an operator, right? I cannot just put number 1 there. So instead I can write identity operator, okay? Identity operator, and minus I H bar over H bar T. It's a linear term, right, of the Taylor expansion. It's defined this way, okay, defined this way. And so on. And then these three terms, right, you can continue. These terms, it's clear, right? It's clear. The operator's polynomial expansion, and operator square means what? You're applying operator twice, right? So in this expansion, it's clear what it means. It's a definition of the exponentiation of an operator, okay? So it's this is unitary time evolution operator. All right. So it basically represents you have a quantum system, how it changes over time. You can calculate this way, actually. All right. That's an operator you apply to any quantum system. So then your only job is to figure out what is H. Okay, what is H? H is in what form? You figure out H, and then you apply that equation to your quantum state, and then you know how it changes over time. That's how quantum mechanics works. Usually it's difficult to figure out what H is. Okay, so this is too abstract, I think. So let's 1 second, 3 minutes left. Let's continue because we'll need to hurry up a little bit. Apply this time evolution operator to quantum state at time 0, okay? At t equals 0. So we have something like this, okay? And then let's say this is the energy eigenstate, okay? So like just imagine particle in a box problem. And then time evolution. And then we actually know the answer already, right? From our previous learning. It's going to have this phase change terms, right? It will have that. So our formalism in the previous slide is matching that result. Let's see together. So this one is a energy eigenstate of the lowest energy, ground state basically. Energy E1. And then, right, that ground state, if you apply Hamiltonian, what do you get? You get energy eigenstate, you get this eigenstate, eigenfunction form, right? eigenvalue problem form. You have an operator, and then the function itself repeats, and you have some number which is an eigenvalue. So energy eigenvalue problem form. Minutes left, and then what I'm going to do, let me just write this one and finish. We apply this one to this, okay, at time t equals 0. According to our previous slide, the exponentiation of an operator, let me continue up to second order term, and then you can imagine you can continue forever, apply to here. And then what do you get? Okay, our identity operator is going to just give you 1, right? And then you apply h once, you'll get extract e1 once, right? So what you're gonna get is minus I, okay, you get e1 h bar t minus half t square, one second, t square h bar square, and then here you get what, h1 square, right? Because you apply the h twice to our energy eigenstate, you extract e1 twice. So e1 is squared there, you can continue this forever, and then psi 1, and then this is what? Psi 1 e to the minus I e1 h bar t, right? Look at this expression. It's a Taylor series of exponential function. So I just wrote this into this term. And then that's actually recovering what we already have learned from solving Schrödinger equation directly, okay? So we just confirmed that this operator exponentiation is working for our well-known problem. We just did a sanity check. Good. So let's finish here today. Let's continue next time. Yeah, question. Yeah, you ask. Yeah, 말씀하세요.
U에서 V 바꾸는 슬라이드 좀 보여주시겠어요?
이건가?
아까
어디?
XT 보는 것 같습니다.
그러면?
X표 치시는
예, 질문하시죠.
제 질문은요.
예.
그러니까 교수님께서 아까 설명하실 때 그 어떤 베이시스에서 다른 베이시스를 바꿔주는 그 매트릭스가 있고 아니면 같은 베이시스 내에서 콘서트 스테이트를 바꿔주는 매트릭스가 따로 있다고 하시는데 근데 지금 유니터리 매트릭스는 두 개 다 가능하다.
맞습니다. So let me repeat the question. Okay, the student just asked. There are two different ways of thinking, right? Changing basis and then actually changing the quantum state itself. And then he was asking, is it correct to say that unitary matrix is being applied to both? The answer is yes, and they have to be unitary transformation for both. Okay, you cannot do something else. Unitary matrix is for both applications, okay? Change basis, you use unitary matrix, okay? And then the second one, you change. Otherwise, there is a problem with the Born rule. Okay, when you change the quantum state into another, also stick with the unitary transformation. Otherwise, your quantum mechanics interpretation, so basically Copenhagen interpretations, will start having a problem. So always stick with the unitary transformation for both applications. Okay, but unitary transformation literally means what? U dagger is identity matrix, right? Both application use both, stick with unitary. Okay, let's finish. Thank you. 예, 질문하십시오. 예.